Good morning, class. We are looking at section 1, angles and their measures. In OpenStax would be 5.1. So we are going to look at angles, trigonometric functions, the unit circle approach, properties of trig functions, and the objectives. We're going to convert between decimal and degrees, find length of an arc, convert degrees to radians and vice versa, find the area of a sector, find the linear speed of an object traveling in a circular motion. Here's the properties of logs. I'm going to remind you what we have seen before. One of them, that is logs. And as you can see here, this is the definition of a log. Properties of log in general. Common log when the base is 10. Natural log when the base is e. Change of base formula, and some properties of exponential and logarithmic equations. This is just to remind you some of the stuff we've done. Now, what we are going to do, let's look at the synopsis of some of the definitions. We're going to look at vertex, line, ray, initial side, terminal side, positive angle, which is CCW, counterclockwise. Negative one is clockwise, standard position. So let's quickly start with all those definitions are very straightforward. This is a line which goes indefinitely on both sides. The thickness is considered to be 0. But half a line or half line, in essence, this point would be the vertex, and it's called a ray. So you have the initial side, and then you have the terminal side, and this is the angle that it makes. Because it's going counterclockwise, it's considered positive. By the way, again, if you put them in slide mode, you can see things step by step. On the other hand, if we go clockwise, it's considered a negative angle, clockwise. Now, this is going counterclockwise, and it's going to go more than one revolution. It is still, of course, a positive angle. When we have the initial side on the x-axis, the vertex on the origin, then the angle it makes with the terminal side, this is in standard position. And in this case, going counterclockwise is considered positive. This is still a standard position, but because it's in a different direction, namely clockwise, it's considered a negative angle. So a line, ray, half line, this is the vertex, and this is the standard position, initial side along the x-axis, vertex on the origin, and the angle it makes with the terminal side. If it's counterclockwise, it is considered to be a positive side. If it's clockwise, CW, that's on the negative side. Let's look at quadrantal angles, right angle, straight angle. Let's see what we have here. There's really not much brand new here. You all remember the quadrants from algebra. So we have a grid, and here's the first quadrant, the second quadrant, the third, and the fourth. As far as trigonometric functions are concerned, In this quadrant, the angle is between 0 and 90. In this quadrant, this is 90 degrees, by the way. This is 0, 90, 180, 270, and 90 corresponds to pi over 2. 180 degrees corresponds to pi. And 270 degrees corresponds to 3 pi over 2, and 360 degrees corresponds to 2 pi, just to refresh your memory. So in the first quadrant, the angle is between 0 and 90, over here 90 to 180, or you can say pi over 2 to pi. In the third quadrant, between 180 and 270, in the fourth one, between 270 and 360 degrees. What do we mean by quadrantal angles? Quadrantal angles have a terminal side that lies on either the x or y axis. The x-axis meaning 0 or 180 degrees. The y-axis meaning 90 or 270 degrees. So these are examples. As you can see, whether we say 360 degrees or 0 actually is the same. So the quadrantal angles, in this case, 360 degrees, 90 degrees, 180 degrees, 270 degrees. So a simple definition of a quadrantal angle, the terminal side is on the x or the y-axis. That's all there is to it. All right, very straightforward so far. Let's look at more of this stuff. In this example, we see that theta lies in the second quadrant because it's between 90 and 180 degrees, the terminal side. Here's the fourth quadrant because the terminal side is between 270 and 360 degrees. That's where it lies. This is an example of a quadrantal angle. To be specific, is 270 degrees or 3 pi over 2. Here's the vertex. If the terminal side and the initial side are at top of each other, we have a complete revolution, which corresponds to 360 degrees or 2 pi radians. A complete revolution, 360 degrees or 2 pi radians. We have a terminal side along, you can think of it as a y-axis that gives you the right angle, which is 1/4 of the revolution or 90 degrees, or 1/4 of 360 degrees is 90 degrees. If we are looking at this angle, making 180 degrees or pi, the initial side along the positive side of the x-axis, the terminal side along the negative side of the x-axis, and the vertex is right here. This is considered a straight angle, half of revolution, that means half of 360 or half of 2 pi. It's 180 degrees or pi radians. Either way is fine. All right, so we've looked at quadrants, quadrantal angles, right angle, straight angle. We've looked at the standard position of an angle, positive going counterclockwise, negative going clockwise. Let's look at some examples. We want to draw a 45-degree angle. Generally speaking, we start with the standard position, which means the initial side is along the x-axis, and we make a 45-degree angle. That would be making it to the terminal side. So vertex, initial side along the x-axis, and then 45 degrees. Now, this has a negative sign. So again, we have the same initial side, and because it's 90 degrees and then negative, you go down and it gives you the terminal side. In essence, negative 90 degrees as far as the value is concerned is the same as positive 270 degrees. Positive 270 degrees. 225 degrees. Perhaps if we do the following, and we remember this corresponds to 180 degrees. This corresponds to 90 degrees. This corresponds to 170 degrees, or 3 pi over 2. We recognize this means if this is the initial side, 225 is between these two numbers. So that would be the terminal side. So 225 degrees in the positive direction. In the positive direction. And in the negative direction, you can subtract that from 360. You get 135. So just in case, this corresponds to negative 135 degrees. All right, this one is 405. And if you recall, this is 0 or 360 degrees. And so because 405 is larger than that, in essence, you want to subtract the 360 from 405, and then it goes to the first, second, third, or fourth quadrant accordingly. So if you subtract 360 from 405, just to give you an idea, if I subtract 360 degrees, gives me 45 degrees. So it's the same as 45 degrees counterclockwise, the positive side. Okay. We want to convert between decimal and degree, minute, second, and so on. So first and foremost, you said counterclockwise, CCW, that is the positive side. If you have one complete revolution, corresponds to 360 degrees. One complete revolution, one CCW, counterclockwise. 1 degree, this means degree. 1 degree, 60 minutes. 1 minute, 60 seconds. You have 1 prime, that means minutes. You have double prime, that means seconds. So that's the first thing. So again, a complete revolution, 360 degrees, 1 minute 60, 1 degree 60 minutes, 1 minute 60 seconds. Now, we want to convert 40 degrees, 12 minutes, 5 seconds to a decimal. In other words, it will be 40 point what? Degrees. That's the concept. Okay. And so we're going to use the fact that, for example, 12 minutes is a portion of a degree. And remember, 1 degree is 60 minutes, so this has to be divided by 60, so on and so forth. So here's how we deal with that. 1 degree is 60 minutes, so 1 minute is 1 over 60 degrees. Okay, 1 second is 1 over 60 times 1 over 60 degrees. I hope you understand why, because 1 minute is 60 seconds. So we are going the reverse process. Okay, so with that being the case, we are going to change the minutes to degrees using this and change the seconds to degrees using this. So 40 minutes plus 40 degrees plus 12 minutes plus 5 seconds. This 12 minutes means 12 times 1 over 60 degrees. This 5 seconds means 5 seconds times the product of these two, 1 over 60 times 1 over 60. And now basically use a calculator. You do the math, you add them up. So this becomes 0.2, this becomes 0.0014, add them all up, and it becomes, so 40 minutes, 40 degrees, 12 minutes, 5 seconds is equal to 40.2014 degrees. Now reverse process. What if we have, and normally we don't want it like this, we want it in this format. What if we have in degrees, but this portion, which is not 1 degree, we want to change it to minutes and seconds, minutes and seconds. So reverse process. So first of all, this is 78 plus 0.562, and 0.562 degrees, if we multiply it by 60, this portion becomes minutes. This portion becomes minutes. So 78 degrees plus however many minutes here. We multiply by 60 minutes. Now this means 78 degrees, 33.72 minutes. We don't like the 0.72, so we know 1 minute is 60 seconds. So we're going to multiply this portion by 60 and change it to seconds. So 78 plus 33 plus 0.72. This 0.72, which is in minutes, we're going to multiply by 60 to make it into seconds. When we do that, here's what we get. So 78 degrees, 33 minutes, 43.2 seconds. And normally we just round this accordingly. If it's 43.2 becomes 43. If it's 43.5 or larger, it becomes 46. We don't go with decimals for seconds anymore. Normally we don't. Needless to say, in some instances, you may need an exact answer, and that's a different story. So, in short, and to recap, a whole revolution is 360 degrees or 2 pi radians. 1 degree is 60 minutes. 1 minute is 60 seconds. Therefore, 1 degree is 3,600 seconds. Okay, because 60 times 60 in case. So on this page, we learned how to go back and forth. So we've done that. All right, let's move on. First, radians and the definition. what is the meaning and definition of a radian? The measure of a central angle subtending an arc equal in length to the radius, which becomes almost 60 degrees. This is very close to 60 degrees. It's 180 over pi or 57.3 degrees, meaning if you take a look at any circle with any radius, this arc length that has the same length as the radius, or if you look at the larger one, this arc length happened to be 3, the radius happened to be 3. If it's equal to the radius, the angle that it makes, which is known as the central angle, I need a space between these two. The central angle is defined as 1 radian. So a quick recap. 1 radian is defined as the measure of a central angle, okay, whose arc length is equal to the radius of the circle of interest. All right. So to find the arc length, we know the formula is S equals R theta, and the proof is very simple. Theta over theta 1 is S over S sub 1. If we were to compare these two, this S means the length of this portion of the arc. S sub 1 is this portion. And if you look at the circumference, that would be also S, but it's a complete circle, and we know that to be 2 pi r. We know the circumference is equal to 2 pi r, where 2 pi is a complete revolution, or just a theta. That's why if C is 2 pi r, and we know that 2 pi is a complete revolution, and we take it to be the value for theta, therefore S is r theta by that comparison. So a quick recap. What is the circumference of any circle? C equals 2 pi r. What is 2 pi? The measure of a complete revolution, theta. Therefore, S equals r theta. For any arc, the arc length is the product of the radius and the angle in radians. For example, we want to find the length of an arc of a circle of radius 4. So r is 4 meters subtended by a central angle of 0.5 radians. What I want to emphasize is that it must be in radians. If it's in degrees, so be it. You just change it to radians. Must be changed to radians. And the units for that would be the units of the radius when you multiply. So when we multiply these two, 4 times 0.5 becomes 2. And the units we use are the units for the radius. All right, I'm going to convert degrees to radians and vice versa. Again, 1 revolution is 2 pi radians or 360 degrees. Therefore, if we divide by 2, we get to 180 degrees being equal to pi radians. And 1 degree, therefore, would be pi divided by 180 radians, and 1 radian would be 180 divided by pi degrees. So I hope it's straightforward as to how we arrive at this. And it gives us this relationship. I want you to pay attention to what we are going to do here. Since 180 degrees is equal to pi radians, d over 180 is r over pi. So if the degrees is given, let's say 50 degrees, you put it here, you find our cross product. If the radians is given, pi over 3 or just 2 radians or whatever, you put it here and the cross product. That's all there is to it. You can also say R is pi over 180 times degrees. Okay, let me just write those just so you know. One might say, if I'm interested in finding R, would be pi over 180 times D, times the amount of degrees. If I want to find D, is 180 divided by pi times the value of R. So everything in one shot, we have it here. Now there are some common angles. I think most everybody knows 0 degrees is the same. 30 is pi over 6. 45 is pi over 4, 60 is pi over 3, 90 is pi over 2, 120 is 2 pi over 3, 135 is 3 pi over 4, 155 pi over 6, 180 is pi, and the rest of them. Those are common angles. We probably have seen them too often not to remember, but if we don't, just as long as you remember this part, you can easily convert the other one. Remember, 30 degrees means pi over 6. So if it's a multiple of 30 degrees, you multiply by this number. Okay. Just for the sake of argument, it's 120 degrees. 120 divided by 30 is 4. So multiply this one by 4. Or if you know 60 degrees is pi over 3, so 120, you multiply this one by 2, and you get to this answer. 45 degrees is pi over 4. So as long as you know these three, I think you should be in good shape, because the rest, common arcs, of course, are multiples of those. And obviously not everything is common arc. All right, we want to convert from one format to the next. So we're going to use that was said. If we are going from degrees to radians, what we can do, for example, this one, replace the D with 30 and find the missing R. Or as I mentioned, one easy way, multiply by pi over 180. Multiply this one by pi over 180, because that's 1 degree. Okay, you can do that. It may go faster. I'm going to assume we are comfortable with the concept. So the first one, when you do that, you end up with pi over 6 radians. You already know that, but in case you're looking at common arcs. And 120 degrees, we multiply again by pi over 180. And we end up with 2 pi over 3. Again, those are common arcs. We know that. Negative 60, it's negative pi over 3. I don't spend too much time on that because I'm hoping this is boring. You remember this stuff. Now, 104 is not a common arc. So you go through the process. And at this point, you can actually use a calculator with a bunch of decimals, because remember, pi is approximated by 3.14. And I want to make sure everybody understands what I mean by that. Pi is not equal to 3.14. Pi is equal to 3.14159, and it continues indefinitely. So if you use a calculator, it gives you a bunch of decimals. And how many decimals? Whatever they ask you, you use. Going back from radians, we want to go to degrees. So we are going to multiply by 180 over pi, or just put it in this formula. Replace the R with negative pi over 2 and find D, or multiply by 180 over pi, whatever is easier for you. Clearly, the pi's cancel each other and we get negative 90. You probably know, again, it's a common arc. Pi over 2 is 90 degrees. Negative makes it negative 90 degrees. We do the same thing here. So, or as I mentioned, you can use it here. With this formula, you can put it here. Okay. If we use this one here, the pi's cancel out. 180 cancels out, the 6 becomes 30 times 5, 150 degrees. And 5 radians. Now again, at this point, we need a calculator because we don't have a pi to cancel out. So 5 times 180 divided by pi, and remember pi is this, and you use a bunch of decimals, however many that they ask you. So 5 radians corresponds to 286.48 degrees. By the way, remember pi is about 3.14, so 2 pi is 6.28 radians, roughly 6.28 radians corresponds to 360 degrees. And again, that's rough. Let's look at some applications here. The latitude of a location L is the angle formed by a ray drawn from the center of the Earth to the equator. So center to the equator. And a ray drawn from the center of Earth to L. So the latitude for this is this angle. Glasgow, Montana is due north of Albuquerque, New Mexico. Find the distance between Glasgow approximately is located at 48.15 degrees or 48 degrees 9 minutes north latitude, and Albuquerque is at 35.083 degrees or 35 degrees 5 minutes north latitude. Assume the Earth radius is about this much, close to 4,000 miles. So 3,960 miles, and we want to find the distance between the two. It's important to understand we are looking at S equals R theta in essence. So it looks something like this. If you look at Glasgow, you can calculate for each one, you can calculate the S, and then the difference between the two would be the distance. So the best course of action is look at the central angles between the two cities, means the difference between the two angles, and we're going to keep it in degrees. We're not going to use the minutes, and then we're going to change the degrees to radians. Remember that. So the first and foremost, the difference in latitude is the difference in their angles. So 48.15 minus 35.083. I'm assuming everybody can use a calculator or just do it by hand. And so the degree difference between the two cities, okay, is this much. And that really refers to this portion. Let me just keep this here so you see. This portion. Okay, so all we have to do, find this distance. How do we find this distance? S equals R theta. What is R? 3960. What is theta? Change this to radians. How? The easy way out, multiply by pi over 180 and use bunch of decimals. So we're going to multiply this one by pi over 180 to go with radians. And I'm using the formula that I have here. S equals R theta. S equals R theta. Here's the R. Here's the theta. Their product. And what are the units? Before we go over the units, whatever the units that you see here. About 903 miles. That's how it's calculated. All right, the next thing we want to look at, we want to find the area of a sector of a circle formed by a central angle theta. And the formula is 1/2 R squared theta. Here's the justification for that. So you're looking at this sector area and this sector area. Okay, this is called the sector. And the ratio between the two thetas, the two angles, theta and theta 1, is the same as the ratio between this area and this area. We know the area of a circle is pi r squared. And why are we using half of 2 pi? Because a whole revolution, we need the whole revolution for a circle, is 2 pi radians. So half of 2 pi. Now I can replace the 2 pi with theta, because 2 pi represents theta as far as a circle is concerned. And therefore, this is the proof that the area of a sector is 1/2 r squared theta, 1/2 r squared theta. So, for example, we want to find the area of a sector of a circle of radius 5. So we have r feet formed by an angle of 60 degrees, and we have theta. But remember, theta must be in radians. And we all know that 60 degrees is pi over 3. We know that. So you don't have to change that. You already know that it's a common arc. I don't expect you to show work for that. But if it's not a common arc, then you have to actually calculate it. So we are going to use the formula 1/2 r squared theta, where r is 5 and theta is pi over 3. Now use a calculator. This is the exact answer, and roughly this much. And what are the units? Take a look at the units for the radius. You use the same units. All right, we have a similar question. The radius is 2 feet. The angle is 30 degrees. Again, 30 degrees, everybody knows, is pi over 6 radians. So 1/2 r squared theta, and replace the r with 2 and theta with pi over 6. And it gives you pi over 3 precisely and roughly 1.05. And as I mentioned, we are going to use the same unit as the radius. So precise answer. It's a good practice to have both answers. So we know what's an arc length. We know what's an area of a sector. And so let's look at a couple more things now. Find the linear speed of an object traveling in circular motion. The linear speed is the good old distance over time. So suppose that an object moves on a circle of radius r at a constant speed. If s is the distance traveled in time t on this circle, then the linear speed, the v, is given as follows. Distance over time, everybody. And the distance we cover is what? S. The arc length is the distance over the time t. So the linear speed is defined as s over t. Angular velocity, the angular speed omega, the Greek lowercase letter omega of this object, is the angle theta, this angle, measured in radians, swept out, divided by the elapsed time. That is, omega is the amount of angle over time, v is the amount of distance over time. So we want to be very clear as to what they mean. So angular speed, linear speed. Now, What we can do, we can see the relationship between the two. We know that V is S over T and S, the arc length, is R theta. And if we separate this into R times theta over T, we know theta over T is omega, so R omega. So the relationship between linear velocity and angular velocity is that when you multiply the angular velocity by the radius, you get the linear velocity. That's a very important relationship. So the linear velocity is R omega, and we're going to look at a bunch of examples involving that. All right. We want to find the linear speed. A child is spinning a rock at the end of a 3-foot rope at the rate of 160 RPM, revolutions per minute. We want to find the linear speed of the rock when it is released in miles per hour. So ultimately, we want to go with miles per hour. So we remember that 1 mile is 5,280 feet. We don't want to worry about that yet. We want to look at the concept, and then it's a simple algebra to go from one unit to the next. But for now, what is a given? We know that the radius is 3 feet and 160 revolutions per minute RPM is omega. So R is 3 feet, omega is 100 revolutions per minute, and V, the velocity or the linear velocity, is missing. And I put some formulas here to remind you. Omega is defined as theta over T, and it is the product of 2 pi times RPM. It could be revolutions per minute. Sometimes we have RPS, revolutions per second. We may even have RPH, revolutions per hour, or even RPD, the revolutions per day. So whatever the units of time is. And remember, a whole revolution is what? 2 pi. That's why if you have RPM revolutions, if you have 5 revolutions, that means 5 times 2 pi per minute. That means 10 pi per minute. That's the concept. It's important to see why we get this, because revolution means a whole circle, which means 2 pi radians. That's why we have this formula, 2 pi times this R stands for revolution. So with that being the case, when we multiply this, okay, the product of these two will change it to radians per whatever this unit is. So this, it is extremely important to know that when we go with that, the units of RPM changes to radians. And I'm going to write PM per minute because it could be RPD, revolutions per day, or RPS. With that being the case, let's calculate the omega, 2 pi times RPM. And the RPM is 160. So we multiply the two and we end up with 320 pi radians per minute. So this is our omega, or the angular velocity. So the angular velocity was given. All we did, we changed the units. So please, again, understand when we multiply by 2, we are changing the units. We are not changing anything, just the units. And now we know V is R omega. So R and then omega in radians per minute. And so we get 960 pi. And if we go with a bunch of decimals, 3016 feet per minute. Now, we would be done here if it wasn't asked for miles per hour. So we have to change this to this format. Otherwise, we are done. And now it's a basic algebra. So it's got nothing to do with this course, but understanding the relationship between miles and feet, because it's in feet. So 1 mile is 5,280 feet. And then minutes, 1 hour is 60 minutes. So here's how it works. We have feet per minute, and we want to end up with miles per hour. So we have to change it accordingly to take care of the feet. We're going to say 1 mile over 5,280 feet, or vice versa. Because we want to get rid of FT, we're going to put the FT at the bottom. So 1 mile goes at top, 5,280 feet goes at the bottom. Please understand, you can go vice versa because this is a unity, this is equal to 1. Why do we put this at the bottom? Because we want the feet cancel each other. And then we go with an hour. We know 1 hour is 60 minutes because the minutes is at the bottom. And we want to get rid of it. We put 60 minutes at top, 1 hour at the bottom. And all you have to do, just multiply these numbers. So 3016 times 1 times 60 divided by 5,280. And that gives us this answer. And the units are miles per hour. I went over this with details because I wanted you to see the unit conversion, which is really not too bad. Unit conversion. All right, an object is traveling around a circle with a radius of 8 inches. If in 40 seconds, a central angle of 1/3 radian is swept out, what are the linear and angular speed of the object? So here's the circular motion. Here's the radius, which is 8. So we're going to write, anytime you have a word problem, write the given. So R is 8 inches. In 40 seconds, when time is 40 seconds, there's a central angle of 1/3 radians. So theta, this theta is 1/3 radian that takes place over the course of 40 seconds. And now we want to see what is the V and omega. So the radius is 8. Over the course of 40 seconds, theta becomes 1/3 of a radian. We want to find omega and V, and omega is theta over T, or 2 pi times RPM. V is S over T, or R omega. So we're going to stick with this formula and say omega is theta over T, where we have theta 1/3 radians, when we have T 40 seconds. So when we do that, it becomes 1 over 120. And it's the precise answer, and this becomes 0.008 radians per second. So that's our omega. V is R omega. Basically multiply this one by omega. V equals R omega. Multiply this one, it's better to use the exact answer, and it becomes 1 over 15. And again, roughly 0.067, and the units, inches per second. So basically, whatever the units are here, remember radians in essence has no units. So because R is in inches, becomes inches per second, inches per second. The minute hand of a clock is 6 inches long. Part A, how far does its tip move in 15 minutes? How about 25 minutes? So here's the minute hand. And by the way, 15 minutes, some of you already know it's 60 minutes, the total, and therefore it's like 1/4 of a revolution. And that is pi over 2. But let's quickly go over that because we need to see what is given. The radius is given. The radius of the minute hand is 6 inches. And for part A, we're talking about 15 minutes. We need to calculate the theta and then S. So R is 6 inches. In part A, 15 minutes, we have to figure out the theta and the S. And by the way, 15 minutes, we already know it's pi over 2. But how do we know that? Just to remind you how we show the work. Theta is 15 over 60. Okay. It's 15 minutes over 60 minutes. That would be the portion of a revolution. A revolution is 2 pi radians. So 15 over 60 means 1/4 of a revolution, which is 1/4 of a 2 pi, which is pi over 2 radians. Now this is in radians. And how far does it move? That means calculate S equals R theta. R is 6 inches, theta is pi over 2. So the precise answer is 3 pi. With a bunch of decimals is 9.42. What units do we use? The units of the radius. Now part B repeats itself. We just figure out this value, theta, for 25 minutes. So instead of 15, we're going to use 25. So part B is being repeated. We are just changing the 15 minutes to 25 minutes. So which is 5 over 12 times 2 pi ReV revolution. And that's the angle. We're going to multiply this by R to find S. 5 pi is the precise answer. 15.71 is a rough estimate, and the units are the units of the radius. So the tip moves that much, moves 9.42 inches in the case of 15 minutes and 15.71 inches in the case of 25 minutes, as long as the radius is 6 inches. A 40-inch pendulum swings 20 degrees each second. How far does its tip move each second? So again, what is given? A 40-inch pendulum, that means the radius is 40. And 20 degrees, that's the theta. And we want to find S. The only thing that I want to remind you, remember, this has to be in radians. It has to be in radians. So we can multiply this by pi over 180, and it becomes pi over 9 radians. S is R theta. S is R theta. So plug in. R is 40. Theta, we found it to be pi over 9. This is the exact answer. This is the approximation, the units of the radius. So 13.96, almost 14 inches. So almost 14 inches. We are looking at the distance. A water sprinkler is to cover a field of 100 square yards. So we want to cover this much in the shape of a sector of a circle of radius 5 yards. What is the angle needed for this rotation? And they are interested in 2 decimals. Okay. So the very first thing, class, is to see what is given. This, it's important to know you're dealing with word problems, so we're going to write what's given. This is the area of a sector. Area is 100 square yards. The radius R is 5. Theta is missing. So this is the translation of the question, class. What is given? What is missing? And we know A is 1/2 R squared theta. So we use this formula to find the missing theta. So we're going to use A equals 1/2 R squared theta. Replace the R with 5, replace the A with 100, and theta is missing. This is 225 divided by 2. is 112.5. So 100 divided by 112.5 is the value in radians, or 8/9. Now, normally they're interested in the answer in degrees. So all you have to do, multiply this one by 180 over pi, or just go with this formula. R is 8/9, find the missing d. However, I mean, you do this, conversion. So it's almost 51 degrees, 50.93, or almost 51 degrees. A windshield wiper's arm and its blade are 30-inch long. If the blade is 24 inches long and the wiper sweeps about an angle of 125 degrees, how much window area can it clean? Again, 2 decimal places. Let's make sure we understand the question. So here's the whole thing, the wiper. This portion of it is the arm, and this portion of it is the blade that actually cleans up. That's why this portion shows the windows and this portion doesn't. So all we have to do, calculate the area of the sector with the radius being the whole thing, which is 30 inches. And then calculate the area of the sector, the gray region, with this being the radius, which is 30 minus 24, or 6. And their difference is what we are interested in. So here's what's given. R1, that means this. This is R1. R1 is 30 inches. And R2 is really this one. Which is 30 minus 24. The angle is 125 degrees. We want to find the area. So we find the area with the larger radius. We find the area with the smaller radius for the gray area, and that's what we are looking for. So as long as we understand the concept, it becomes a piece of cake. So I hope you realize the given and the concept. And everything is written here. Of course, theta must be changed to radians. Okay, so R1 is 30. R2 is R1, which is 30 minus 24, 6 inches. And theta is 125 degrees, and we change it to radians by multiplying by pi over 180. So here's R1. Here's R2, 6 inches. Here's theta, 125 degrees, converted to radians. So now plug in. Everything is just a simple math now. Plug in, everybody. So let's plug in. Replace the R1 with 30, theta with 25 over 36, R2 with 6, and just use a calculator for that. And the area has the units of the radius squared, whatever the units are. So 942.48 inch squared. So I hope everybody is clear. Again, whenever you do word problem, you want to dissect the problem, so understand what you're dealing with. We're going to do as many questions as we can. An object is traveling around the circle of radius 2 meters. It travels 5 meters in 20 seconds. What are the angular and linear speeds? So that's what we are going to do. We are going in a circular motion. The radius is 2 meters. It travels 5 meters in 20 seconds. That means S is 5 meters. T is 20 seconds. You want to find the V and omega. So that's the translation. Pay attention to what I write as the given. We are dealing with word problems. As long as you write the given, it works out like a charm. So V is S over T. V is S over T. So 5 over 20. So 1/4. And you use the units accordingly. Meters per second. The velocity or the linear velocity is 1/4 meters per second. But what is the angular velocity? Okay, we know V equals R omega, so omega must be V over R. V is R omega, omega is V over R. We have this. Let's divide it by R, which is a 2. And it becomes 1/8. By the way, notice the units. I want to put the units so you see how this thing works. It's 1/4 meter per second, and this is meters. So you get per second. Because you know you're dealing with angles, you go with radians per second. So I hope you see that the units do work. All right, a centrifuge or a centrifugal force ride similar to the gravitron and amusement ride spins at 22 revolutions per minute. If the diameter of the ride is 12 meters, what is the linear speed of the passengers in kilometers per hour? Again, this one has to be taken care of at the end. It's just a conversion. We don't worry about that for now. But what is given? We read the question, spins at 22 revolutions per minute. This is your omega. And remember, this is RPM. And it has to be multiplied by 2 pi to become in radians per minute. So omega is given as 22 RPM. And the radius is 12 divided by 2 or 6 meters. Okay, because this is the diameters. 12 divided by 2, 12 divided by 2. I hope everybody understands why. And we are looking for the velocity. So first and foremost, omega is in RPM. Anytime you have revolutions per minute, you have to immediately multiply by 2 pi because a whole revolution is what? 2 pi radians. So let's do that. And that gives us 44 pi radians per minute. Again, we're going to keep the pi for now. So V is R omega and R is 6. So you multiply this one by 6. That's all you have to do. So when we multiply, notice what happens. This is the precise answer, 264 pi, and it's meters per minute. Okay, why meters? Because the units of the radius were meters. And we are done here, except this unit conversion has to take place. I'm going to assume everybody knows how to do that. We're going to go over that in a moment. But please understand, right here, we are done. We are done here. We just want to change this to the units that they asked us to do. And so the unit conversion is that we want to write this as kilometers per hour. Okay, and so how do we do that? We have 264 pi meters per minute. We say 1 kilometer over 1,000 meters. Okay, and remember, because you want to calculate you want to cancel out the meters. Now, per minute, remember 60 minutes is equal to 1 hour. Because we want the hour at the bottom, we put the minute at top, so it cancels this one, 60 minutes over 1 hour. Okay, and now you do the math with the pi with a bunch of decimals, so it's almost 50 kilometers per hour. That's pretty fast, 50 kilometers per hour, almost. A DVD drive has a maximum speed of 7,200 RPM. If a DVD has a diameter of 12 centimeters, what is the linear speed in kilometers per hour of a 0.5 centimeters from the disk center? This is really what matters. Where are we located at 5 centimeters from the disk? Doesn't matter how long, the diameter or even the radius is. The radius is 6, but at 5. So this is the R, and it's spinning at 5400 RPM. So that's omega. We want V. V equals R omega. Remember, RPM, we have to multiply this one by 2 pi. We have to multiply this one by 2 pi. So this is the answer. Radians per minute, that's omega. V is R omega. So we multiply this one by R, which is 5, and it becomes centimeters per minute. And again, we are done. We are done here. But we want to change it to kilometers per hour. And we do that. 1 meter is 100 centimeters. 1 hour is 60 minutes. 1 kilometer is 1,000 meters. And we do that, we come up with the following answer. Okay, 1 kilometer is 1,000 meters. So that is the one that needs to be fixed. And so there you have it. It's very straightforward, everybody. So we are repeating the same type of questions and again. So let's do this one. The radius of each wheel of a car is 15 inches. If the wheels are turning at a rate of 3 RPS, revolutions per second, how fast is the car moving? Express your answer in inches per second and miles per hour. Okay, first and foremost, the radius is 15 and omega is 3 RPS, and I can't emphasize this enough. The moment you see revolution, you have to multiply it by 2 pi to make it in radians. I want to quickly look at this one more question. So let's finish this. And so we got that V equals R omega. Let's multiply the two. And this is again done. This is done. And to go to miles per hour. So this is done. To go to miles per hour, we do the conversion. So we've done the conversion. I don't want to spend too much time on it. It's 90 pi. I want to go with the precise answer, 90 pi inches per second. You multiply 1 foot is 12 inches, 1 mile is 5280 feet, and 1 hour is 3600 seconds. Remember, 60 times 60. When you do that, becomes 16.1 miles per hour. I want to look at the last question, and the rest of them you can do it on your own. I want to quickly look at one more question. This conversion, I'm assuming everybody can see how it's done. Okay. It was an elementary algebra. The mean distance of Earth from the Sun is 9.29 times 10 to the power of 7 miles. Assuming that the orbit of Earth around the Sun is circular and that one revolution takes 365 days, find the linear speed of Earth in miles per hour. So quickly, what is given is the radius R, and then omega. Okay, one revolution takes 365 days. So omega is one revolution per 365 days. So we have revolution per year. We want to change this to revolution per day. we want to change this to revolution per hour, okay? So that's the idea. So omega is defined as theta over t, which is 1 revolution per 365 days, right? We have a complete revolution. It takes 365 is rough. So it's 1 revolution is equal to what? 2 pi radians. So we're going to replace the 1 revolution with 2 pi radians. So that's omega. 2 pi over 365 radians over days. Now, 1 day is how many hours? 24 hours. So 1 day over 24 hours. So this one is the units of radians per days. And 1 day is 24 hours. The reason we put the day at top because these two cancel each other. Take a look. So we have now radians per hour. So what is at top? At top is 20 pi. At the bottom is 365 times 24. We can cancel out the 2 with 24. So that's what we have precisely. Okay, this is radians per hour. So we got the omega with the units of interest, radians per hour. So V's are omega. V's are omega. We multiply by the radius of 9.29 times 10 to the power of 7. And that is the speed. If you do the math, you end up with 66,633.324 miles per hour. So close to 67,000 miles per hour.